So step 1, identify the unstable thing. When I say almost, I mean basically always. You're almost always going to react the unstable thing in the first arrow. So in this case, that's our H+. Now we need to identify what reacts with it. And then we compare. So we have two different sets of lone pairs. We have them on a carbonyl oxygen, and we have them on alcohol oxygen. And the carbonyl oxygen is always more basic. It's more reactive. The reason is you have a good resonance structure with a lot of O- on that oxygen because of the double bond. Whereas with the alcohol, we don't have that. Now, the difference is pretty small. It can go on either. Check the carbonyl first. So I wanted to make sure that the charged thing, the H+, the most unstable thing, was involved in my first arrow. It was. And I have generated a positively charged carbonyl. Involved. Yeah, actually, there's a lot of examples, Melitza, where that could potentially happen. And I think what you have to do is you take a look at them and go, does anything happen if I do this? Does anything happen if I do that? And compare them. So we can actually go back and see what could happen if we did the other one. Chitra said, should we always compare resonance structures for finding the most reactive site? Yes. I'm trying to think if I can think of any no's, and I can't. So yes. Okay. Now, in the previous example we did last class, we used an alcohol solvent to attack the positively charged oxygen because, and it's up to you, you can draw the resonance structure of this molecule I have drawn here, and you'll have a positive carbon at the carbonyl, and that is fine. I think we did that in the last example. I'm not going to do that right now. It's not necessary to do. If it helps you, do it. If it doesn't help you, don't do it. I am using the internal nucleophile to attack my electrophile. So it's not quite what you need to be doing on that, but identify possible reaction sites, compare them. Remember to watch out for rings. I like rings. It's not just me. Nature really likes rings. And so there are an awful lot of rings. More resonance equals more reactive site. If everything's neutral, Alyssa, often. I think we'll get a feel for this, and we'll have to go through a lot of examples. Is this all in equilibrium? Yeah, absolutely. Everything. Yeah, thank you, Lauren. You're absolutely right. This is all in equilibrium. All these things involve when you're breaking and forming bonds that are more or less equivalent are almost always in equilibrium. And here we're breaking oxygen-carbon bonds and forming oxygen-carbon bonds, so it's going to be in equilibrium. So we form this. Now, what I'm going to do is going to use an equivalent of ethanol that we have in solution, because again, our most reactive thing is this H plus here. It's the species because it's charged. The problem is the only kind of reaction that this thing can really do is to go backwards. We need to really get rid of that H plus and move it around. We're going to do a trade where a molecule of ethanol is going to pick it up. So ethanol has become positively charged. Now, again, we're looking at what the most unstable thing is. The most unstable thing is this positively charged ethanol. We have here, we have a hemiacetal. Talked about these last class. It's a case where you have two oxygens bonded to the same carbon. One is an ether, one is an alcohol. That is not a stable way to be. This particular case with the six-membered ring is like a unique special thing. This is actually all sugars are like this. What I've drawn here is the basis of glucose, sucrose, fructose, all the sugars that we eat, keep our brains going, and are currently trying to figure out what the hell is going on, and you're being fed by sugar, and they're all hemiacetals. But hemiacetals in general are not stable. And so we have a choice of a lot of lone pairs. In this case, we don't have any carbonyls. They're all the same. If we put it back on the oxygen as in the ring, we go right back to where we were, and we can go backwards, and that's great. But if we put it on the other oxygen, maybe we can go forwards. And again, notice what we've done here is we've taken a few steps to basically move a proton from one oxygen to another. Okay. How you know when you use equilibrium arrows or regular arrows? I think for all this stuff we're talking about with these acetal kind of chemistries, if the bond strengths being formed and broken are about the same, you're not making a particularly strong bond, you're not breaking a particularly weak bond, the arrows are should always be equilibrium. If you are forming like a carbon-carbon bond at the expense of a carbon-oxygen double bond, you're making a really, really strong bond. Carbon-carbon bonds are really, really strong. Those are not really reversible. You don't see a lot of C minus floating around, so it's not really reversible. You don't see a lot of H minus floating around. That's not reversible with the reductions that we saw. but all this oxygen carbon stuff is really mealy and can go back and forward, so it's an equilibrium. Yes, that was exactly where I was going to, Christian. This is a proton transfer. You could have equivalently written, I would accept this now for full marks without you fully drawing all the mechanisms. If you just wrote proton transfer, and did that, and sort of saved yourself a few structures of drawing, I would accept that immediately. I'd also accept if you wrote this as plus minus H plus, means the same thing. I'll also accept it if you write PT for proton transfer. Not P, capital P, small t, which would be platinum. That's, I accept all that. Yeah, there's still a hydrogen, but the hydrogen is implied. I don't need to draw it in. I will. But it's there because nothing else funky is going on. That's why we spend so much time practicing drawing stuff, is because when we draw this, it becomes really clunky to draw all the hydrogens. So hopefully you can just glance at something, you can guess if it's charged, you kind of see the hydrogens now. I know we're moving fast through this term. Okay, so from this guy over here, can anyone guess what the next arrow is? So Madison asks, how do we know to put this into a ring? Always watch out for things where you can make 5, 6, or 7 membered rings. They will almost always form. If they're possible to form, they will. In this case, we had an alcohol nucleophile that was able to make a 6-membered ring. We're going to see a lot more examples of this, so hopefully this is going to click in the next little bit. This I'd say is an advanced example. This would be, it'd be fair game for a final exam, but it would be kind of a toughie. So anyone have any idea of what we do next from that final structure on the far right? Ethanol takes an H off the oxygen. That's definitely possible to do, Christian, but then we just go right back to where we were on the second last structure. You're right. That actually probably happens a lot, but it's not productive. It just goes right back to where we were. Can you make water? Yes. Perfect, Faith. We love making water. How do I make water? To make water, I need to break this carbon-oxygen bond, right? So let's do that. Perfect. Okay, so let's say that perfect. Great, we have water. And then this carbon is now going to be positively charged. And it's right next to the lone pairs on oxygen. And so we would prefer to draw that as a resonance structure. Just kind of skipping around because it's going to be a little bit hard to just, my pen is pretty shitty. Notice I'm now drawing a resonance structure, non-equilibrium structure. And if I compare those two resonance structures, hopefully we agree that the bottom one is a better resonance structure because all the atoms have their full octet. But now, is this a stable molecule? How do you know it's not a stable molecule, Fatima? I agree with you. Or Madison, if anyone wants to say why it's not stable. Yes, Samantha, absolutely need to get rid of the charge. If you have a charge on your molecule, you're almost certainly not stable. You're not done yet. So if that tells you got more work to do. The only thing that we really have going on here is if you think about it, it's a little hard to see, but this thing we've got here is very similar to this thing up here, also with the purple line. We have an oxygen making 3 bonds and positively charged. And we're going to release that charge in exactly the same way. Now, we're not going to make another ring. There's no other ring to make. But we have lots and lots of ethanol present. How do we know we have lots of ethanol present? Because I told you that we had like 100,000 equivalents or whatever. And so the ethanol is going to attack that carbon. Why that carbon and not the oxygen? 2 reasons. One is always react from your second most stable resonance structure. The second reason is the oxygen already, you might forget about it, but it has a lone pair on it still. That does not look like a lone pair, it looks like a single electron. The oxygen is already using 4 orbitals. It can't accept more electrons. It already has all 4 orbitals filled. But if we attack the carbon, then we're in good shape. And for the same reason, we're not done yet because we still have a positive charge, as everybody's pointing out. So we need to get rid of that. And the way we get rid of that is almost the inverse of our first step. Where that's an ethyl group. Now we've reached a point where stable. This is the first point where we're completely stable, that the hemiacetal we have up here wasn't awful. Everything else was charged ever since we started. So everything else wasn't a stopping point. We had to move forward. We had to move forward. The hemiacetal, depending on the conditions, might have been the end point. And we can think about why that would be in the end point. If instead of ethanol, I'd had water present, the hemiacetal would have been our endpoint. Because as Lauren and Faith, I think, were pointing out, we're forming water here. And the reason we're able to form water is because of Le Chatelier's principle. We're essentially trading a water for an ethanol. And that makes sense because this reaction is being done in ethanol. There's a lot of ethanol, there's not a lot of water. We prefer to add ethanols to things and add waters to things. But if the reaction was done in water, we're not going to want to give up water. There's tons of water. There's also nothing to trade it for. You're just stuck with water. So Katie, so are we always trying to make the end product neutral, or do we want to match the charge of the starting material? You always want to make the end product neutral. At some point a little bit later in the course, I'm going to show an example where that's not the case, and I'll highlight why. But for 99.9% of all the stuff in this course, your final answer is going to be neutral. It's only when we're trying to draw resonance structures at the beginning of the course where we had some stupid-ass molecules, because I was trying to prove a point about resonance, where we saw things that were charged all the way through. Almost all the time, your end product is going to be neutral. If it's not neutral, it's a salt, and we don't get a lot of organic salts. So if you have a charge, you're not done. And I wish I could give you like a long list of everything we can do. I can't. It's one reason why I'll create practice problems for these guys. But it's one reason why there's so many effing practice problems. I would work through all the practice problems in chapter 7 of the Top Hat textbook, because a lot of them are going to be on things like this. Now, let's take this approach and let's think back to maybe a slightly earlier example, because this is actually a lot of arrows. This is complex. Like if you're thinking like, oh god, it gets harder from here. It doesn't. It doesn't. This is a lot. This is about as many arrows in a row as we'll draw. So let's go back to this, I think, which is pretty much the first example we started with. So if we take these ideas, what we need to recognize is what is the most reactive species in here. And everything looks neutral by inspection when you first look at it. But is everything neutral? Or are we kind of lying to you with the way that things are drawn? I'd say the question for this is provide the mechanism, provide the product. I'm going to actually just redraw it very quickly. So Melissa said CH3 is negative and unstable, and she's absolutely right. Right? Like when you see lithium salts of something, in your mind, you should be drawing it that way. Would we put equilibrium arrows at the start for this particular example or the last example? Last example was equilibrium arrows the whole way through. This example, this is showing the scheme. So I'm showing the scheme, so we're not necessarily providing a mechanism. Once we start doing the mechanism, let's think about whether it's reversible or not. Okay. So we identify the really reactive component. What's going to react? It's the CH3 minus. So this is highly reactive. It's going to want to do something. What we have is we need to figure out what it's going to react with, what its reactive partner is. So any guesses on that? Okay, we got a positive Jesse says carbon, Aiden says oxygen, Melissa says positive carbon. Iosite says sp2 hybridized carbon. So we have a lot of different answers. I like all those you guys who are saying carbon. The carbonyl carbon. Yes, I like that. So let's just be, Melissa, I like your answer positive carbon, but let's just remember, and that's fine. I'm sure this is what you're thinking, and you're right. Just remember it's not positive, it's electron deficient because of the resonance structure with the negative charge on the oxygen. But the carbon itself isn't quite positive, but it's got positive tendencies. So either way, you guys are all right. The oxygen is negative because remember, delta positive, delta negative, because of the resonance structure. We have a minus charge. A minus charge is not going to react to the positive charge. A minus charge is not going to react to the minus charge. It's going to react to the positive charge. So we're going to have this. Okay, so let's come back to Madeline's question over whether we should put equilibrium arrows here. Is this reaction readily reversible? Let's think what we had. So we had sort of CH3 minus and a carbonyl. And on the right-hand side, we have this O minus species. Is C minus and O minus, are they about the same level of stability? No, like there's no resonance on a C minus or anything, right? It's just C minus. Yeah, we formed a carbon-carbon bond. Yeah, O minus is better, so it's not reversible. And it's not better by a little bit, it's better by a lot. Like O minus is good. C minus is bad. And we formed a carbon-carbon bond, and those are very unlikely to be reversible. Now, it's almost never wrong to write an equilibrium arrow in that everything to a certain degree is in some form of equilibrium. But it's essentially not reversible. Yeah, so everyone is coming to this, or both Fatima and Melissa come to the same conclusion. That's a not reversible reaction. Different ways, both of them are perfectly valid. Okay, so now we have a little bit of acid and water. And what we're doing with this is we literally dump in some acid and water into your reaction mixture. And you'll do this if you do this in the lab. And the reason is that right now we have this charged species. Like the counter ion for this is lithium. But lithium oxygen is like a really ionic bond, right? That's not stable. And yeah, it's a salt and you can do that, but we don't want that. We probably want the alcohol. So we treat this with a little bit of H plus in water. And again, we can look at the unstable things and it's the O minus and the H plus. This one's pretty simple. O minus get H plus. Oops. That is not what that forms. That's, I don't know where that came from. Okay, now I've got a question for you, tying into what we were covering right before this lecture. Is that a stereocenter? Let's assume R is sec-butyl. I'm just picking something random. It doesn't change anything we've just drawn. But my question isn't possible. Does anyone think it's not a stereocenter? I can feel almost the relief going, this is a question I know. I got this one now. It is, right? You're attached to 4 different things. Okay. Was the one we started with, was that a stereocenter? No, you're right. It's a stereocenter. That's a stereocenter. There's the one we started with, the stereocenter. I love the exclamation mark, Samantha. Yeah, it's not, right? It's an sp2 carbon. Double bonded to a carbonyl. It's not attached to 4 different things. It's not a stereocenter. You can't assign RRS to that sp2 carbon. So we made a stereocenter. Okay. Question for you. I haven't drawn this RRS, right? I've drawn straight lines. I haven't assigned it RRS. So let's say there are 3 options. This center is one of these 3 things. It is 100% R. It is 100% S. Call that A. Let's call that B. Or it is 50-50. Call it option C. No, you guys know this, and this all plays into this stuff. Let's think about this. Do you think this new center we've just developed, do you think it's 100% R, 100% S, or 50-50 R and S? Well, there goes the confidence booster, Jesse. You did. Okay, Olivia's answering the previous question. There we go. No, sorry. 50%. These are 100% of the molecules. Let's say we had 1,000 molecules do this reaction. Are there? So sorry. That's a really good question. How can a center be both? It can't. Let's say where there are 1,000 R, 1,000 S, or 500 R and 500 S. So 500 of them are. I don't know if anyone wants to change their answer. Sorry, that was unclear. I completely agree with you. Wouldn't it depend on how the CH3 attacks? Brilliant, Melitza. That is exactly the answer. It depends on how the CH3 attacks. Okay. So let's talk a little bit about how the CH3 attacks. I'm introducing a concept here. This is going to be a little bit mind-blowing. Not because it's so incredible, but because it's just we're bringing back a concept we covered and it's coming back in. The reason I'm doing this isn't so much necessarily it makes a ton of sense now, but we are going to be talking a lot about this in the next bunch of class when we start talking about carbon-carbon double bonds. So I'm going to just draw an energy diagram, and I'm going to draw the sigma bond. Oh God, this shit again. Yes, this shit again. Of the carbonyl. Sorry, I'm a moron. Pi bond, pi alert. The reason is that Chemistry always happens at the frontiers of occupied orbitals and unoccupied orbitals, because we have electrons in some of those, and the unoccupied ones that are lowest energy are the ones most likely to accept electrons. I don't know if you go back to one of the early lectures I posted. I didn't do it in this thing, but it's on the lectures. I started talking about making hydrogen H2 and breaking H2 because you add extra electrons. So if we look at the carbonyl bond and we look at what that looks like, I'm exaggerating a little bit for effect, but the lobes look like this in there. The oxygen lobes are going to be bigger because oxygen is electronegative, and so more of the electron density is going to be around on oxygen. This is like the Lcao model, linear combination of atomic orbitals. If I want to draw kind of as a molecular orbital, it's going to look something like that. Where I've kind of fused the orbitals together and showing the electron density in the bond. Okay. The antibonding orbitals, we invert the size. So the carbon's got the big ones, and the oxygen's got the little ones. And they're out of phase, of course, because it's an antibond, and so you can't make a filled-in phase with the non-filled-in phase. You can't make a bond there. Same thing at the top. So that's why that's sort of an antibonding for a p orbital. So what's happening in all these reactions we've just seen with the carbonyl attacks, and let's say we draw on two hydrogens here just to keep it real simple. Let's not draw any sp orbitals because they're just going to be confusing. But, you know, one's coming out of the page, one's going into the page. In every single one of these cases where we've had a carbonyl react with hydride, with oxygen, with carbon, doesn't matter, the same thing happens. What we've done is our nucleophile has come in, you know, whatever it is. Let's say it's a CH3 minus in this case. It's got lone pairs, and it's taking those two electrons and it is dumping them into the antibonding orbital. And by doing that, it breaks the carbon-oxygen double bond because we put electrons into the antibonding orbital. And when you put electrons into an antibonding orbital, you break a bond. And that's what breaks the double bond and pushes the electrons onto oxygen. Okay. How does it do that on this molecule? Well, what it has to do is it has to, like, it exists as an orbital, right? If for the CH3, for example, that lone pair is in an sp3 orbital. Right? It has to be. Carbon's is using 4 orbitals. It's using 3 to make bonds to hydrogen. It's using 1 as a lone pair. It must be sp3. And what it's doing is I guess I should do unshaded with unshaded. It's attacking that big, juicy, empty p pi star orbital. This is, look, like they're kind of pathetic on the pi orbital and they're full anyways. On the pi star, the ones on carbon are bigger than the ones on oxygen, so that's why you attack the carbon. There's a lot of reasons and everything just kind of lines up, but fundamentally it's because the lack of electron density is felt stronger on the carbon. That's why you attack the carbon. I arbitrarily Drew that as an unfilled orbital. Okay, let's just think about this for just a moment. I'm going to redraw what we just had there, except this time I'm going to use a precise example of what we had in the way of a molecule, which is we had a hydrogen at one site, and on the other site we had, I think it was an isobutyl group. The CH3 minus is coming in. If we attack the bottom one, we get that product. I didn't think this out properly, because if we attack the top one, I'm going to draw it on the bottom. We get this other product. Are those, first of all, do we, looking at this mechanism, looking at attacking the top or the bottom, is there any difference? Like, is there an energy difference? Do you think that there's a preference? Is there a steric reason? Is there an energetic reason why we might attack the top or the bottom? Or does it not matter? They're the same. Jesse says no, there's no difference. Mohammed cages his answer. Wise. Always wise to qualify. The rest of the class stands in silence. Any other votes? Yes, because of steric hindrance, maybe. So Julia, where do you think the steric hindrance would be? That's a fair answer, Samantha. I don't know is a perfectly fair answer. Isn't there supposed to be a difference if there's a change in RNS? Okay, so the answer is no, there's no difference between the energies of attacks. It's the same either way. Let's take a look at this flat as a flat molecule again. Let's just remember what this looks like. And just to drive this point home, for the ice, maybe I shouldn't have picked an isobutyl because it does kind of throw it off a little bit. But the top and the bottom approach on this carbonyl carbon, which is what we're talking about, are equivalent. This is a hydrogen. This can just spin around like a top as much as it wants. There's no difference between the top and the bottom on that carbonyl. They're identical. They're absolutely identical. You have a 50% chance of attacking from the bottom. You have a 50% chance of attacking from the top. Now, if you only do one molecule, like one molecule does it, either did one or the other. But, you know, normally we're talking about, you know, 10 to the 20 molecules. And over that kind of statistical number, you get 50-50. So if we go all the way back, so I guess the second question I've got, so it's a 50-50 chance on the top of the bottom. The second question I've got are A and B the same molecule or are they different molecules? Jesse says enantiomers. Madison says they're the same molecule. So we've got the two possible answers here. And it's a 1-1 tie with a really disappointing 52 of you in this meeting. It says with different. Okay, Madison is switching her vote. Yeah, so they're enantiomers, right? There's one chiral center, one stereocenter, and it's not the same. It's flipped. So they're enantiomers of different molecules. Whenever we attack a carbonyl, there's not an inherent difference of a carbonyl between a top and a bottom. They're the same as far as the carbonyl is concerned. So you generate enantiomers. You generate both of them. You generate a 50-50 mix of the two because there's no preference for attack from the top or the bottom. So you make both the one product and the enantiomer of that product. So it was correct of me to write that with no stereochemistry drawn, or it's correct of me to write it with both stereochemistries drawn. Both of those are correct answers. But doing either one of those two on the bottom is incorrect because you don't get just one, you get the pair. Not defining the stereochemistry tells me you are saying it is a 50-50 mixture. Absolutely, Madison, you're absolutely right on that, by the way. Your rationale is perfect. And I think the rest of everyone here did the same thing. So that's really awesome. So, okay, so why did I take this digression? We're talking about mechanisms. Suddenly we have these molecular orbitals up there. We're talking about angles. We're talking about enantiomers again, where all this coming from. It's because it's all interconnected. One thing I wanted to show here was we just connected, all parts of the course. At the very beginning of the course, we were drawing electron orbital diagrams with electrons moving into different orbitals and geometries and hybridizations. And then we've connected, we did a little bit of resonance in here to think about where that wave was charged. We've drawn mechanism arrows in here to try and figure that out. We had some acid-base chemistry there. Then to determine how this reacted to give us enantiomers or diastereomers, we started talking about stereochemistry. What I want to highlight is we're moving into talking about mechanisms. Everything we have covered is relevant. I didn't cover that so you can forget it. I covered it because it's going to kind of need to be the intuitive tools that you're going to draw on to do this stuff. Sorry, this stuff just builds on everything, which is fun and terrifying. I think it's more fun, but then again, I'm not writing the exams, so that's easy for me to say, isn't it? So I think at this point, what we're going to talk about on Monday, and I believe we have this course on for Monday and Wednesday a little bit. We're going to be talking about esters and amides. We've already talked a little bit about esters. We're going to talk about a little bit about how to make amides from esters. And then we're going to briefly talk about the peptide bond. I'm writing the final. I write the exam. No, I set the exams. You guys write the exams. Melitza, you're absolutely right. This is tough. I think you need to think about at all times. The biggest tip I've got is find out what is the most reactive thing. That's where you're going to react. You're going to try and minimize energy every step of the way. If we go back to this really long example that we did, and we think about minimizing energy over this example, every single one of these steps is trying to minimize energy or is paired with something to minimize energy. So Julia, I see your point. I will, you know what, I need to create a Carbonyl practice assignment anyways. I'll post that. I won't have the answer keys up. I'll write that tomorrow morning first thing as my first chance to get something. Is I've got a couple of hours tomorrow between 5 a.m. and 7 a.m. I'll write it up in the morning, so I'll have it posted by relatively early in the morning, and I'll try and get some answer keys up there for that next week. But again, tackle the Top Hat Chapter 7 problems. So in here, we have an H+. We're able to stabilize the H+ by attaching it to an oxygen. We've stabilized that a bit. We're then able to do the ring closing and move this around. How did this stabilize it? Well, actually, what we had was a decrease in entropy because suddenly things are tied up a little bit better. We have an H+, we want to stabilize the H+, we can remove it to solvent. These are all kind of an equal trade. Now this is kind of stable, this hemiacetal is kind of stable, but what we're relying on again is entropy and Le Chatelier's principle. There's a lot of ethanol in solution, there's not a lot of water. And so I can switch the H+ from being on ethanol where it's on oxygen to being on another oxygen. It's more or less an equal trade. And if I do that, and I admit this is a tough example. I admit this whole thing is a tough example. I can get something that can produce water, and we really jumped on that. Making water is a good thing. Again, is entropically downhill. We've now added water to something that is swimming in a bath of ethanol. Now we have a carbocation here. We're stabilizing it by resonance. And then we can get rid of this carbocation. We get rid of this thing that even only part of the time is still a 6-electron carbon by attacking it with ethanol. Now it's protonated. We need to get rid of that. We wash it off with ethanol and we get something that is the first time. It's the most stable thing in this entire sequence. This is all under equilibrium. It's all under what we call thermodynamic control. It's going to find the minimum energy point. The minimum energy point is here. And so that's where we end up. So at all points, what we're trying to do is deal with the most charged thing. We can deal with that if we have a much simpler example like this guy here. This was the charged thing. We need to find the thing that's most likely to react with. That was the carbonyl. We reacted with the carbonyl. Oh shit, we have an O-. What can I do with it? Well, nothing with this CH3 lithium. But luckily there's a second step where we add water and acid. And we can react the most reactive thing with the most reactive thing to get something that's neutral. And we're probably done if we're neutral. I'm going to do a lot more examples of these. So I will post some practice problems on Saturday. Again, the answer keys aren't going to go up till next week, but at least you'll be able to work through some stuff and start thinking about some of these problems. Take a look at the lectures. Chapter 7 in the Top Hat textbook is a good place to go. Those of you who like Khan Academy probably love it, and it's great. Those of you who hate it will hate it, and that's fine too. But again, you can look up some carbonyl chemistry on that. I think those are the places to start. If you've done all that and you still have questions, come back. We're doing chapter 7 right here. This is all on carbonyls. We're going to talk about esters, then we're going to jump back to chapter 6. Sorry. It's in the textbook. It's in my. I need to check the syllabus. I think we're on chapter 7, and we're going to go to chapter 8. Just to be clear, you drew the removal of water as resonance. I drew the removal of water as a forward arrow, and then the next step was resonance. The water came off here, and so this was an arrow, and I have water to the side, but the water's already off. I'm drawing this as the resonance. The water's already gone by that point. The water left under this equilibrium arrow here. Yeah. Yeah, because you're right. I can't draw the removal of water as resonance because you're not allowed breaking sigma bonds with resonance. Can't move atoms. Okay. We're at 2:30. I gotta run. I'm sure you guys do too. Have a great weekend. Yeah, Jeanette, so Jeanette has a really important point here. I feel like my understanding is mediocre as we learn, but then like before the exam, everything kind of falls together and makes more sense. My goal is I'm trying to set the exams at these points where things come together. Like the problem is it would be really nice if I said, look, we have optimized the best way to teach everyone organic chemistry. This is the order that we do things in. It works for 90% of people and things go in. And I can say that we don't know. There's an awful lot of research into how to best teach organic chemistry, and every single one of those things comes into a different answer. So which tells you if you have lots of answers to a problem, it tells you none of them are very good. So none of them are very good ways and orders to teach it. We try and make this course a complete thing. So by the end of it, hopefully everything's kind of clicking. But I think we're going to need to see it from different angles, and I don't know when this is going to click for you. Some of you are probably looking at this going, I get it. This makes quite a lot of sense to me. A lot of you, it's going to take a lot more examples and lectures, and we're going to be talking about more of this stuff. We're going to be approaching it from a different angle, and you'll come back to it and go, oh, that now makes sense to me. So all I can say is don't give up. Keep trying. It will click. If you, in all the years I've been teaching it, I've had one student who it never clicked for, who honestly tried really quite hard. They still walked out with a pretty decent grade. I think it was a B. But and I felt really bad because I tried to spend a lot of time with it because it's just that near the end of the class it just wasn't clicking, and I felt awful because they were doing everything. But some of our brains just don't work for this. But most of you are not that one student. Like that's 1 out of thousands. And if you guys are here doing this, you're all trying. So keep at it. It will click. I promise. It is hard. I promise you at the beginning of the course, this was hard. It is hard. You're not stupid. This is just hard. So hopefully it does come together. Anyways, have a good weekend. Don't fret too much. Good luck. Enjoy Halloween. Though this does not look like a fun Halloween day. This isn't drinking outside weather. Oh well. We'll survive. Take care. Bye.